Welcome to Lab 1, Constant Velocity. This is the table of contents, and first is the introduction. The purpose of this experiment is to observe the motion of an object, or in this case a car, that is moving at the same speed without changing direction, or in other words, at a constant velocity, and then we'll compare those observations to a computational model. Before doing this experiment, I made the assumptions that there are negligible friction, negligible air resistance, and negligible motion in axes other than the x-axis in order to maintain a net force of 0 and also to make sure that I'm only looking at the motion in the x-axis. And then some key concepts I used were Newton's first law, which basically stated that an object in motion would remain in motion unless acted on by an external force. So in this case, to have something at a constant velocity, I would need a net force of 0. And using the velocity update formula, if the net force was 0, then the final velocity would equal the initial velocity, meaning that the velocity would stay same throughout the entire experiment. And using that in the position update formula, the average velocity would end up being the same all throughout, which would mean that there would be a constant change in position over time, which is the definition of a constant velocity, and that is the model that we're going to be using for this experiment. And this is going to be a preview of what the results should look like. The initial velocity should be same as the final velocity, and there should be a constant change in position throughout the entire experiment. So for each same time interval, there'll be a same amount of position covered. And now onto the experiment. First is the free body diagram, where the black box in the car is going to represent the car in the experiment. And we're starting at t equals 0 seconds, so that is when it's moving at a constant velocity, which would mean that there's no net force. So the only two forces acting on this object are the normal force acting upwards and force of gravity acting downwards. And the system is going to be just the car that's moving at the constant velocity, and the surroundings is going to be everything else. And this is the tracker video analysis. So it's when I click the center of mass as the car was moving to record its position over time. And now we're going on to the data analysis. So on the left is the data table that I collected directly from Tracker. And notice how each time step is 1/30th of a second, and I'll be using that in the computational model. And then I generated a graph from this and found the slope, because from these equations you can see that the slope of a position time graph is going to give you the velocity. And I got a velocity of 0.311 from the line of best fit of this graph. And then I created a computational model starting with the initial conditions from Tracker as shown at the top. And then I set up the initial position, the initial velocity, and the initial time, as well as the change in time that we saw before on the last slide. And then within the loop for every time step, I set the final velocity equal to the initial velocity, which is constant velocity as shown in the velocity update formula, as well as put in the position update formula where I updated the position at a constant rate. And then the full code can be found at this link if you would like to look at it. And now this is the comparison graph of the tracker analysis in blue compared to the computational analysis in red. Next, I'll be going into analysis of this graph in the discussion. So the velocities shown in both the computational and tracker analyses were very similar to each other, and this is an expected outcome because I was modeling the observation. And the computational model did offset a little bit from the tracker data in certain instances, which could be due to external forces acting on the car, like friction that wasn't accounted for, or maybe a gust of wind from the air conditioning. Now onto potential errors. And this could be external forces such as friction acting on the car, which could impact the net force that was observed and impact the velocity. And also not consistently selecting the center of mass accurately when doing the tracker analysis. That could result in wrong positions being collected, which would result in wrong velocities being calculated. And also errors when rounding that reduces accuracy, and then not taking the motion into other axes into account because that would impact the position that was recorded. And now into further questions, first being the what if the axes were flipped question. This would mean that the data is reflected on the axis, so the positive position values would be negative and vice versa, and this would also affect the slope of the graph because the position is included in this position over time is the slope, so the velocity would end up being negative, but all the magnitudes of everything would be the same, just the signs of the position and velocity graphs and the velocity values would be flipped. And If it's possible to know how many forces are added together to give it that net zero, no. I'm aware of the normal force and the gravity acting in opposite directions, and those ones are balancing out, but we are not sure if there are any more forces because of how many things the system is touching. So many other forces could act in a completely other directions. We know that there's air resistance and friction, but we don't know what other forces could counteract those forces to keep it at net zero. And on to the conclusion, which is that a constant velocity can be simulated with a system that has a net force of 0, and we can construct a computational model for this, and at each time step the velocity would stay constant, and that computational model would accurately match up with our physical observation at constant velocity.